through some notes today covering magnetic fields, basically introducing what magnetic fields are, thinking about how magnetic fields affect charged particles, whether we're talking about charged particles like protons or electrons or other charged objects, or we're talking about current in a wire. So I'm going to go through basically an entire chapter here in the notes. I'll do some example problems, draw some pictures, that sort of stuff. So I'm going to go ahead and get started. First thing is what is a magnetic field? So when we use the term magnetic field, what are we referring to? How does it relate to stuff that we've talked about before? The first thing that I want to point out is that magnetic fields are formed when you have moving charges. So charges have to be in motion to generate magnetic field. We will talk about that later. Magnetic fields can also affect moving charges. And that's primarily what we're going to start with, is thinking about what happens when charged particles move in the presence of an external magnetic field. And then we'll talk about that interplay a little bit later. So that's basically the order in which we're going to cover things in magnetism. We're going to talk about how magnetic fields affect moving charges. We're going to talk about how moving charges generate magnetic fields. And then we're going to talk about the interplay, that induction that happens when you have moving charges create magnetic fields, and then those magnetic fields affect moving charges, and that interplay between those two ideas of charge and electric fields and magnetic fields interacting with one another. So in order for us to talk about magnetic fields, we're going to kind of define what they are first and talk about how we measure them. So we have a couple different units we use to measure magnetic field. Generally, we're going to use Teslas as our unit for magnetic field. That's going to be our standard SI unit. Almost always we're going to deal with Tesla. Now, a Tesla is the same as a Newton per coulometer per second. So you see Tesla, our SI unit, is the same as a Newton per coulometer per second, which looks pretty complicated, and I guess it is. And also, we could consider that a Newton per amp meter. So again, we're going to talk about these units and where they come from and how, say, amps and newtons are going to relate back to Tesla soon. Another common unit we use for measuring magnetic field is the Gauss. A Gauss is a smaller unit, a smaller scale measure of magnetic field, which is probably good because a 1 Tesla magnetic field is actually a ridiculously strong magnetic field. So a lot of times we're going to be using, say, like 10 to the negative 4 Tesla or something like that to talk about a magnetic field strength. And so if you want to have a non-SI unit of measure to work with, that would be the Gauss. So 1 Tesla is equal to 10 to the 4th Gauss of magnetic field. Usually we're using Tesla, though, in all of our problem solving. So let's talk about what magnetic fields look like. So magnetic fields are generated by magnetic dipoles. So a magnetic dipole is a combination of a north and south end of a magnet. Just like positive and negative for charges, north and south, really completely arbitrary. Meaning that the only thing that I want to get across here is that we have two different types, two different ends of this magnetic dipole. We have a north end and a south end. Let's see. So with our north end of the magnet, the bar magnet here, and our south end of the bar magnet here, this magnetic dipole generates magnetic field lines. It generates a magnetic field which we represent using magnetic field lines. So our magnetic field lines always form continuous loops when we're dealing with magnetic field. So I'm going to draw some loops here. The magnetic field emanates outward from the positive end. It loops back around and comes back inward at the south end of our bar magnet. So this is what these loops look like. And these magnetic field loops are going to be important in helping us understand what the magnetic forces are on the object. The magnetic field lines themselves are just a tool we use to understand the forces acting on charged particles. But we're going to need to start by being able to draw and designate what those magnetic field lines look like. If you've ever taken like a compass and tried to line it up with Earth's magnetic field, you're going to see that little piece of metal kind of waver around and line itself up in a specific direction. That's something that is orienting itself relative to this magnetic field because there's a force applied on objects due to an external magnetic field. So A couple key points here about our magnetic field lines is they form continuous loops and they loop outward. The direction is designated as away from the north end of a magnet and inward at the south end of a magnet, always forming these continuous loops. Now, the next thing I want to show you is that sometimes these drawings that show up, like in textbooks, are really, really bad and are misrepresenting what a magnetic field looks like. So you may see drawings of bar magnets and the magnetic fields around them that look like this. These actually came from middle school science text, an electronic version. And it looks pretty bad, right? There's an issue with it, and that is that the way that the magnetic field lines are drawn is as if they stop when it touches the bar magnet, okay? They move outward, and then they stop here. Now, if we were to fix these, we would show that a magnetic field line actually loops all the way through. There is a magnetic field generated inside this bar magnet. So if you had a charged particle inside that bar magnet, it would be experiencing a magnetic force. So we're going to talk about pretty soon. So again, we always have continuous loops for our magnetic field lines. This is, of course, really different than what we saw with electric field lines. Remember, with electric field lines, they always were originating on a positive charge and landing and ending on a negative charge. So we have the positive charge as the source of electric field lines, and the negative charge is the sink for electric field lines. Magnetic field lines are a little bit different. Now, this bar magnet over here, that's drawn in a very unfortunate way because it's not realistic. What this should look like is that we have our magnetic field lines, of course, going away from our north end and towards our south end of the magnet, but really they should continue all the way through and form a continuous loop. Even in the middle of your bar magnet, you should have magnetic field lines because they always form loops. Let's talk about electromagnets. In an electromagnet, you are using a current-carrying wire to generate a magnetic field. Often, you want a really uniform magnetic field. Those are created by stacking loops of wire, coils of wire together, and forming inside that system a very uniform magnetic field. Now, even in this case where we have stacks of wire looped together, you could get a region where you have a very uniform magnetic field inside that system, okay, right in the middle. A lot like what we saw with electric field lines, the density and spacing of the magnetic field lines can give us some indication of the magnetic field strength. So what we would be looking at here is a case where, well, inside this electromagnet, we have a fairly uniform and directed upward magnetic field. So it's pretty uniform in there. That is possible to generate a uniform magnetic field, and we'll talk about how to do that a little bit later on when we do some labs. All right. Again, an electromagnet with some loops of coil of wire is generally how we make a uniform magnetic field. Here's an illustration for you. This is showing the magnetic field of the Earth. And the question is, well, what's wrong with the picture? So you've got some magnetic field lines around the Earth. Okay, so I've got some of these field lines, and they loop around, and they come over here and stop. And these loop around this way, they come here and stop. Changes we want to make to this? Again, this is an illustration from a textbook. Big problem here. Two big problems here, actually. These field lines should be continuous. Okay, so these should loop all the way through. Even through the middle of the Earth, we have magnetic field lines generated. There's another issue, though. And if you look carefully, you notice that this at the top was designated as north, and this was designated as south. It's It's not the way it works though, because our magnetic field lines are going to emanate outward from the north end of the magnet and they're going to land on the south end of our magnet. So we actually should flip these. This should be our north end of our bar magnet if we treat the Earth as a giant bar magnet. And this would be the south end of our giant bar magnets. Again, north and south are totally arbitrary, but they do have a distinct direction. So north is what we designate as that end at which our magnetic field lines are generated as being directed outward, and south is where they're being directed inward. The Earth's magnetic field has definitely flipped in the history of Earth. It may flip again, we don't really know, but it's just kind of a cool thing that the Earth's magnetic field does. So if you hold up like a compass or something like that, you are aligning it with the Earth's the magnetic field lines that are emanating around Earth, because Earth itself basically acts, I guess if we want to simplify it, it acts a lot like a giant bar magnet. Yeah, so this is, I guess, a little bit better of a drawing, but still lacks the connection of these lines through the Earth, right? So they should connect all the way through. And if you have a compass, and you take your compass outside, you line it up, and you'll get this little arrow that's going to point this way. Okay? This little arrow here, the north end of this bar magnet, is pointing towards the south end of the magnetic field generated by the Earth. So that you can always align with that direction. You can always know which way is magnetic north for the Earth. Now, thinking about the forces that magnetic fields apply on objects. So again, the magnetic field helps us understand and talk about forces that are going to act on an object, in the same way that gravitational fields helped us get a better understanding of gravitational forces. And electric fields allow us to understand electric forces. Magnetic fields are going to give us a picture for how we're going to expect magnetic forces to be applied on charged particles. Now, magnetic forces, it turns out, are kind of weird. They have some unusual behavior that we're going to want to describe and talk about a little bit here. A couple things that magnetic forces can do. Magnetic forces can accelerate charged particles by changing their direction. They can cause charged particles to move in a circular or helical path. However, magnetic forces can never change the speed or kinetic energy of charged particles. In addition, magnetic forces can never do work on charged particles. This seems kind of weird. We can accelerate an object but not change its kinetic energy, not change its speed. Well, really, magnetic forces, in the way that they are applied and how they're applied on an object, magnetic forces tend to be described as centripetal forces. So they always are going to act towards the center of a circular path. And so we might need to use this formula once again for centripetal forces. That's probably going to come up a lot in your quest problems, some of the problem solving that we're going to do for the next several days. Now, if we want to write a function, an equation to describe the force that charged particles exert on, that magnetic fields exert on charged particles, our equation is right here. So this force here, that magnetic force, is equal to the charge of an object multiplied by its velocity crossed with the field strength. Magnetic force is a vector quantity. We have here a cross product. So that cross product might help you see that, or I guess maybe see why it is that we're thinking about this as a circular motion problem. You might be able to see that Coulomb force, the magnetic force that's going to be applied, that Lorentz force is always going to be perpendicular to the magnetic field. It's also always going to be perpendicular to the direction of motion of the particle. And if our force acting on an object is always perpendicular to its direction of motion, then we might change the direction of motion, but we won't change the magnitude of that velocity, which is why we're not changing the speed of an object. When we have no alignment with our acceleration or our velocity vectors, we're going to have an object moving in a circular or helical path. So Q in there is the charge in coulombs on the particle that's in motion. V is its speed in meters per second. B is the magnetic field, and again, we're in SI units, so we're thinking about it as in Tesla. So this cross product here, I don't know if you remember doing cross products in pre-cal or if you do them at all in calculus. You can use your typical cross product formulation if you want. We also, though, can definitely also use, let's see, I guess I don't have my other version of this. So if you want to write this just in terms of the magnitude of the vectors involved. So our magnitude of that magnetic force is going to be Q times the magnitude of V times the magnitude of B times the sine of the angle between them. So then I can get the magnitude of that force. I would have to know the direction by doing a cross product or understanding the right-hand rule. So we're going to talk about the right-hand rule today. It's a way of determining what the direction of the product vector is if you know the direction of the first and second vectors that you're multiplying together using the cross product. All right. So let's look at some examples. All right, first problem. We're going to sketch the path and calculate the acceleration. The first thing we have is E equals 2,000 newtons per coulomb. So I've got an electric field here, and I've got a velocity for the particle. So here I've got an electric field, I've got a charged particle. Let's say it has charge Q, just because that's easy. And we're going to think about what's going to happen to this charged particle in these different scenarios. So here I've got a particle, it's stationary, it has a charge of Q on it, and the electric field is directed that way. So let's say the charge is positive as well. That might be worth noting. If our electric field is directed this way and I've got the stationary charged particle here, we might want to remember the relationship between the Coulomb force and electric field. It's Q times E. All right, so if I know that it's a positive charge, I know my electric field is generated that way and in that direction, my Coulomb force is going to be upward as well. So the Coulomb force on this particle looks like that. And if I were to think about the path this particle is going to take, it's going to be moving upward and it's going to be accelerating while it does so. How about this one over here? Electric field is directed this way. It has an initial velocity that is in this direction, towards the right side of the screen. But the Coulomb force in this case hasn't been changed at all. The Coulomb force is still going to be the charge on that particle, Q, positive, times the electric field strength. And again, the electric field strength is the same. So I'm going to have a Coulomb force acting on that object. I've got velocity that way, and I've got a constant force this way. What I'm going to see as a result is going to be a parabolic path. It's going to be speeding up as that happens, because it's now gaining a vertical component to its velocity, even though it has a constant horizontal component to its velocity. Now, this was review, so we were looking at Coulomb force and how that relates to electric field. Now let's try magnetic force. Okay. We're going to sketch the path and calculate the acceleration. We'll get to the calculations in just a second. Let's start with just thinking about path. I know the magnetic field, I know the velocities, and I also know my equation that relates the Lorentz force, or the magnetic force, to these other quantities, Q, V, cross B. All right. First of all, these X's here, that indicates that the magnetic field is pointing into the board, okay? So the direction of the magnetic field is this way. This is going to be a little bit challenging because when we're dealing with magnetic fields, because we're also looking at a cross product, our velocity and magnetic field are always going to be perpendicular to that force that's acting on the particle, which means that we are absolutely going to have to deal in three-dimensional space for pretty much all of the problems that we're going to do for the rest of the quarter. That's kind of challenging. It's especially challenging when I'm trying to do it on a screen and I can't, you're looking at something two-dimensional. But the first thing I want to do is take a look at this problem. So I need to figure out Q times V cross B is. I look here at this particle, and this particle, in this problem, our initial velocity here is 0. If there's no velocity, there's no Lorentz force. There's no magnetic force on this object. And so this object right here experiences no force at all. Stationary particle does not move, does not experience a force in a magnetic field. That's kind of weird, because if this particle is in motion, it will be experiencing a force. The motion of the object contributes to, or has an impact, or plays a role in how strong a force it's experiencing. All right, now over here, I have a velocity in this direction and a magnetic field in this direction. In order for me to understand the direction of the force that's acting on the particle, I'm going to have to understand how to do a cross product, or I'm going to have to use a shorthand notation for this, what we call the right-hand rule. So the way that we do the right-hand rule, I'm going to show you a couple different methods for this. And this is going to allow us to get the direction of the force and the acceleration on the particle. It won't give us the magnitude, but it will give us the direction. So the way we do this right-hand rule is that we think about our cross product here. I've got two vectors that I'm multiplying together. And in order to figure out the direction of the product of those, I need to, I'm going to use my right hand to do that, because basically we're going to create a right-handed coordinate system. And the first thing I do is I take the first vector that's listed in my cross product, and I'm going to take my fingertips of my right hand and I'm going to align them with the direction of that vector. Okay, so V points this way. I'm then going to rotate my wrist so that my fingertips can curl 90 degrees or less towards B. These X's indicate that the magnetic field is pointing into the board. So in order for me to be able to do this cross product, my fingertips point this way and my wrist is oriented this way. So you can see the back of my hand pointing towards you. But V curled B, first vector, second vector, and my thumb gives the direction of the magnetic force that's acting on this particle, or the product of that cross product. So that notation tells me that the magnetic force points that way. There's a couple other ways you can do a right-hand rule. So some people like to do this, where you point your first finger out, you point your second finger inward, and then your thumb gives the direction of the product. So then I, orient my wrist so that my first finger points towards V and my second finger points inward towards B, and then my thumb gives the direction of the force on that positively charged particle, upward. But what's going to happen over time? So originally I have this force upward, but if that force is directed upward, then this velocity is being curved this way. And what happens when our velocity is curved upward a little bit? See, the issue is that because there's a cross product here, it's actually going to change the direction of the force on this charged particle. So if it's some time later, velocity is now directed this way. Well, now when I do my right-hand rule, I align my fingertips with V, I curl my fingertips towards B, and my thumb gives the direction of the force on that charged particle. And now, my force is directed at an angle this way. So that's going to change my velocity even more and make it even steeper, my velocity. So eventually, the velocity might be pointing upward like that. When the velocity is pointing upward like that, I'm going to align my fingertips with V. I'm going to curl my fingertips towards B. And my thumb gives the direction of the force on that charged particle. That looks to me like the direction of the force on that charged particle is continually changing, but always directed inward towards the center of this rotation. If we were to draw the path that that charged particle would take, it would be a circular path. In this case, a counterclockwise circular path. We can also calculate the magnitude. So I know that what's going to happen. I know the direction of this force. And if I wanted to calculate the magnitude of that force, I'm going to use my equation for the Lorentz force, which is that magnetic force is equal to Q V B sine theta. I don't care what Q is. Maybe it's the charge on a proton, 1.602 times 10 to the negative 19 coulombs, multiplied by V, which is 2,000 meters per second, times B, which is 2 Tesla. Sine of theta? Well, that's the angle between V and B. And as drawn, that should be 90 degrees. So sine of theta should give you 1. But you can find the magnitude of the force using this equation. You can use the right-hand rule to find the direction. All right. So with that in mind, let's think about what might happen if we have a current-carrying wire. Instead of just a charged particle just flying through space, what if instead we have current-carrying wires? We know a lot about current-carrying wires now. We can build circuits and all that other fun stuff. If we have a current-carrying wire, then we can use this formulation of the same equation instead. F equals I times L cross with B, where I is the current measured in amps, L is the length in meters of the direction of the current, or I guess like a segment of wire that's carrying current, and B is our magnetic field strength. This actually comes directly from the equation I just gave you. So before we said that magnetic force is equal to Q V cross B. If instead I'd like to be able to talk about current and length of wire, then I've got to make some changes in my equation. Any thoughts? Do you see where it should be? You can try to derive that. One thing you might notice is velocity is basically just meters per second. So you could think about it as the length that some charged particle will travel in a certain amount of time. So this becomes Q L over S cross B, where that L is the length that that charged particle travels through some time. And then you might notice that, well, charge divided by seconds, if I pull those out, and remember that seconds is a scalar quantity, so I can actually pull that away from that cross product. And now I have some current carrying wire, and then some length or direction that charge is flowing, crossed with B, our magnetic field strength, and I've got my equation for the the magnetic force on a current carrying wire. We can try an example problem with that. So let's say a wire carries a current of 2.4 amperes through a uniform magnetic field, 6.1 kilotesla. What is the force on a 0.75 meter long section of the wire if the current moves in the positive x direction? Let's see. I think actually I've got a typo here. I think this should be the z-hat direction. I don't know why there's a k there. But I need a direction in there because it's a magnetic field, so I'm going to make that change. So we have an equation for this already. The magnetic force is I L cross B. If we want, we can just plug in the values and find the magnitude first. If I know how much current there is, 2.4 amps. I know the length of the wire is 0.75 meters. And I know the magnetic field strength, 1.6 Tesla. going to take amps times meters times Teslas, but that's going to give me units of newtons. I need to actually pull out a calculator. I cannot do this one in my head. Times 0.75 times 1.6. Yeah, okay, that seems reasonable. 2.88 newtons of force. Great. Now, if I want to know the direction, I'm going to have to do a cross product. So it says here that the wire moves in the positive x direction and the magnetic field is in the positive z direction. So we're going to want to try to figure out the direction of the force on the charged particle. Now, you might be able to tell already, as we talked about earlier, that the plane that contains L and B is always going to be perpendicular. This force is always going to be perpendicular to the plane that contains these two vectors. So I'm going to draw a right-handed coordinate system to help us out with this. So I'm going to say, so X is pointing out of the board this way. That's the X direction. Y is this way. And Z is upward. That's X, Y, and Z will give you a right-handed coordinate system. So if our current is in the positive X direction, so I'm going to align my fingertips straight outward. And if B, the magnetic field, points in the positive Z direction, I need to be able to curl my fingertips from this position, pointing straight out at you, to straight upward. So I'm going to orient my wrist this way. Now I can curl my fingertips upward, so I've got L cross with B, and my thumb gives the direction of the force on the particle. That means that our force is pointing in the negative y hat direction. It's pointing this way. So this wire that's carrying current in this direction is going to be pushed in this direction in the presence of a magnetic field that points upward. Let's do it the other way. So if we do this method for doing a right-hand rule, I'm going to orient my wrist so that my first finger points along the direction towards L, so that's in the positive X direction. My second finger points upward, okay, and then my thumb points in that direction, okay? So that'll also work. I think that curling my fingertips just is a more natural sort of way of going about this. All right, so I think got another problem to try out. How much current must be flowing through a horizontal 20-meter long wire that's suspended in a 5 Tesla magnetic field if the wire has a mass of 0.2 kilograms. Okay, so I've got this wire. It's 20 meters long. It is suspended in this magnetic field. I don't know the direction of the magnetic field. We might be able to figure that out later. But what I do know is that it has a mass of 0.20 kilograms. And if it's suspended, that means that the net force on it equals 0. And if its net force equals 0, then there must be something balancing the gravitational pull downward. And that's going to be our magnetic force. If I think about the forces acting on this, I've got the force of gravity downward, and I've got the magnetic force balancing that, so it must be directed upward. Now that magnetic force I know is I, L cross B. And I know I know gravitational force is mg. So now I need to just set these forces equal to one another. So let's clear some space. All right. So if these forces are balanced, then mg equals ILB. I'm going to assume that these are perpendicular because that's going to maximize that force. So if I want to find, let's see, how much current? So current is going to be mg over LB. That's it. I would calculate that. Let's see, 0.20 kilograms, and my constant here, 9.8 meters per second squared, all divided by the length. It's 20 meters long, and magnetic field strength, 5 Tesla. I don't know what that is. I'd have to calculate it. Looks like it, yeah. I'll use 9.8. You can do this. If we use 10, we could have done this without the calculator. Maybe you can do it without the calculator anyway. All right, 0.0196 on our units. Yes. If the current is flowing north, in what direction must the magnetic field be? So if this is north, and this might be a little bit tricky because now I guess, swapping around the direction of, here, let's do it this way. Here's our wire. And the current's flowing north. And if this is balancing the gravitational force, then the force on this wire must be up, out of the board, at you. And so the question is, which way is the magnetic field facing? So remember that magnetic force is I, L cross B. So if the current is that way, I'd like the force to be directed that way, so I want my result for my cross product to be pointing outward. I need to have magnetic field pointed this way. So my magnetic field should be pointed in this direction. So doing this, this other way, we're going to have current directed upward. Orient your wrist so that your thumb points upward out of the page, and that means that magnetic field points this way, towards the left. What if we have a loop of wire? We can do torque and we can do magnetic forces in this case too. Now I've got a loop of wire here shown. Let's see. And make sure that you can definitely see it here. I've got it, the wire has current flowing in a specific direction around it. And we're going to try to figure out what the forces are on this wire. Now this looks a little bit complicated because basically it's like I've got 4 separate wire segments. So let's do one segment at a time. Let's think about the force on this segment of wire right here. Well, remember that the force on a current carrying wire is equal to I, L cross B. If the length of the wire, or that segment of wire the current's flowing through, and the magnetic field are aligned, then the cross product has to be 0. So on this segment of wire, from here to here, the magnetic force is 0. That's true up here as well. From this point to this point, as current flows along in this segment, the magnetic force on that section is 0. But on these two sections, we're going to get a force generated because I have current flowing this way and magnetic field this way. And since I know the magnetic force is equal to I, L cross B, if the wire is directed this way and the magnetic force is that way, the magnetic field is that way, my thumb gives the direction of the force on that wire. That's into the board. There is a magnetic force that points into the board here. What happens on this segment though? Now the current is directed this way, the wire is directed this way, the magnetic field is that way. I gotta do like a weird thing here with my cross product. Let's go over here. I'm gonna align my fingertips downward, and I'm gonna curl my fingertips towards magnetic field. My thumb gives the direction of the force. That's this way. On this side, the magnetic field is into the board. On this side, it's out of the board. So I've got one force that way and one force this way, and that's going to cause a net torque on this system. So we can think about this system as potentially spinning around an axis right here in the center. This side is pulled that way, this side is pushed that way. We can actually calculate the net torque generated. So I'm going to clear this all out. Okay, remember that magnetic force is, the magnitude of that force is I, L, B. So if I have, if I want to figure out the net torque on this, that'll equal the torque generated from this side plus the torque generated from that side. Let's back up here. And torque, if you remember from mechanics, is R crossed with that force. In this case, it's going to be magnetic force. So what's R? Well, R is going to be our distance away from our pivot point, which, if this is A, then this is going to be A over 2. So the torque generated on one side of this is going to be A over 2 times I, L, B. What's L? L is going to be the length of that wire. So the torque is going to be A over 2 times I times B times that magnetic field strength. Now, there's two of these. So my net torque, because they're going to act together, this is going to pull into the board, this is going to push outward. And so those torques are going to combine. They're going to tend to spin this system in the same direction. So our net torque is actually the current times A times B times the magnetic field strength. One way of simplifying that is to say that it is equal to I times the area of our current carrying loop times magnetic field strength. Let's see. So here's our loop here. The area of this loop is A multiplied by B. Now, I've shown this for a square loop. It actually happens to work for any type of loop. I'm not going to show that solution though. It's a slightly more complicated solution. You are welcome to explore it further on your own if you want. But if you had a circular loop as well, you could take the current flowing through the circular loop times the area of the loop times the magnetic field strength, again assuming a constant magnetic field strength, and you could solve the problem the same way. All right, we're going to calculate the torque on a 40 centimeter length of wire bent into a square if it carries 20 amps of electrical current and it's perpendicular to a magnetic field of a strength of 0.520 Tesla. And again, if I want to get the torque here, it's going to be current times area times magnetic field strength. So that net torque on this system, actually, you can just call it torque. Torque on this current carrying loop is going to be got 20 amps of current. And I'm going to need its area. I know it's 40 centimeters on a side, 40 centimeters total, and it's bent into a square, so that means that each side must be 10 centimeters, which I'm going to change to 0.10 meters. That's squared. I'm going to multiply that by 0.520 Tesla, and I can solve for my torque. I don't know what it is because I haven't calculated it yet, but it should be pretty quick for us to do that. So 20 times 0.1 squared times 0.520. All right, so I get 0.104. Hopefully you remember what the units of torque are. If you don't remember what the units of torque are, then you'd have to get them from your equation. I could write this as amp meter squared Tesla, which is accurate, but maybe not the most acceptable or most common units we use for torque. I think probably you should write this as Newton meters of torque. I think that is the more appropriate or more, I guess, conventional, but not any less and this isn't any more accurate. This is, it's also amp meter squared Tesla, but Newton meters is more common use. All right. So we're going to talk about how charged particles move when they're uniform magnetic field. There's a couple different types of paths that we could see for particles. So we're going to go through some of that. So let's think about what happens when we have this charge mass M, a mass M, charge Q, and it's moving at speed V, right angles through a magnetic field. Magnetic field B is pointing out of the board at you. We're going to derive an expression for the path of the particle as a function of charge, mass, speed, and magnetic field strength. So hopefully you know already what type of path it's going to take. But I'm just going to go through that again, just as a quick review. So I've got the velocity this way, and I know that the magnetic force, or the Lorentz force that this is going to experience, is equal to the charge times the speed crossed with the magnetic field direction. So V is pointing this way, and B is this way. My thumb gives the direction of the force is downward. It's just kind of hard to orient my wrist that way. So we can do this method as well. So V, curl to B, or point your finger towards B, and your thumb gives the direction of the force on the charged particle. So it's downward. But as this particle changes the direction of its path, because that is a centripetal force, eventually V is pointing this way. And when V is pointing this way, and B is pointing this way, your thumb gives the direction of the force as inward. Now, it points that way. The magnitude hasn't changed. The magnitude of the force is equal to the charge times the speed times the magnetic field strength. Those are all constants. But what has changed is our direction. And so we're going to have this circular path for our particle. But what we notice is that that Lorentz force, that magnetic force, is the inward centripetal force always. So what we're seeing is that magnetic force is a centripetal force. And so QVB equals mv squared over r. That's going to be our central, assumption here, is that this magnetic force is acting as a single contributor to that circular motion. And now we can simplify this equation a little bit. So I can know that I want an expression for the path of the particle. I think we should probably solve for r, okay? One thing to note is that V shows up on both sides. I'm going to simplify that a little bit. And so our radius of curvature for our circular path is going to equal to mv over qb. So as the mass of the particle increases, if I have a heavier particle and everything else is the same, it's going to go through a larger circle. Same as if it's faster. If it has more momentum basically at the start, essentially it's going to be harder for it to turn. It's harder for that magnetic field to turn the particle and change its path and keep it from moving in a straight line direction with its initial momentum and inertia. However, the more charge there is, the stronger the charge is the more it's going to be affected, the bigger the force it's going to experience is. And so that would make for a tighter curve if we have a larger charge on the object. And the same with the magnetic field strength. The stronger magnetic field can pull that charge along more rapidly. Basically, there's three different types of paths that we can see for charged particles. When your velocity is perpendicular to the field, when V and B are perpendicular to one another, you're going to get a circular path. That charged particle is going to move in a single plane, continuously in a circular path. However, if there's any component of the velocity that's parallel to the field, then that component of the velocity is going to be unaffected by the magnetic field. Because remember that magnetic force is equal to QV cross B. Now, these are all vectors here. If there's any component that's parallel, it's unaffected. And so when you have a helical path, it's because you have a circular path with one component of the velocity that's unchanged, constant. And so you have, this is really needs to be in 3 dimensions. I probably should not have drawn it that way. But what I want you to think about with a helical path is almost like taking a slinky and stretching it out. So you'll have a circular path that's actually stretched upward and moving upward because there's a vertical component of velocity that's unaffected by the magnetic field. Or, if your velocity is entirely parallel to the field, you could have a particle that just continues going in a straight line, unaffected. Even though it's in a magnetic field, even though it's a charged particle, it doesn't experience any force whatsoever. So you could have a circular path, you could have a helical path, or you could have a straight line path for a charged particle moving in a magnetic field. And that, I hope, you think is weird. I hope that you're not just taking this all for granted, and you're just accepting that that's what there's an equation there, and then we're done with it. I would like you to think about what that means. That the motion of the charged particle itself is going to help determine what sort of a force it's experiencing, because that is unusual. And I will definitely come back and talk about that later, but I want to get a little bit more background out of the way, because I would have to jump to some modern physics stuff, and we're not going to do that quite yet. All right, so here's a couple pictures that we can think about. We're going to try to figure out what we know about the sign of the charged particle based on its motion. So, in one case here, notice we've got a particle moving in this counterclockwise circular path. We've got one particle that's moving in a straight line path with its velocity here perpendicular to the magnetic field. And then we've got another particle that's moving along this way, clockwise. The first thing I want you to notice is that this one, in order for this particle to move in a line that's perpendicular to our magnetic field, notice our magnetic field is directed into the board. It's shown with all these X's here, saying magnetic field points that way. For this particle to move in that direction, it must be neutral. It cannot be charged. Because we know that the Coulomb force is equal to the Lorentz force, that magnetic force is QV cross B. Let's think about this particle here. In order for this particle, particle 1, to move in this counterclockwise circle, when it's right here at the top, it must be experiencing a force that's still towards the center of rotation. So that means that that magnetic force must point downward. If the magnetic force points downward, then we can deduce from that the direction of the type of charge that's on this particle. Because our magnetic field points inward, and our velocity points this way. So let's check using the right-hand rule. So if I have V and I curl my fingertips towards B, my thumb should give the direction of the force, assuming that this is a positively charged particle. Because notice the Q shows up in our equation. So for a positively charged particle, V curl to B, our thumb gives the direction of the force. This must be a positive charge. But something weird happens over here with particle 2. With particle 2, notice that since it's a curvature this way, our magnetic force must point inward towards the center of that circular path. And if it's directed this way, clockwise, then I know that V points that way. So I know that V is this way, and according to the picture, B is this way, and so our thumb should give the direction of the Lorentz force or magnetic force on a positively charged particle. But our force must be pointing this way, since I know that I get the curvature that results in clockwise rotation. And so that means that the only way that could happen is if V curl to B and our thumb gives the direction this way, but our actual force is in that direction. This must be a negatively charged particle. Because that introduced a negative sign here, and since this is a vector equation, that would explain that direction as being opposite what we'd expect for a positive charge. There's a couple different ways to think about this. If you use the right-hand rule for your negatively charged particles, you could say, oh, I'm going to align my fingertips with V, curl my fingertips towards B. Thumb gives a direction that's opposite the expected force for a negative charge. You can do it that way. There's also the possibility of doing a left-hand rule, and so you always use your right hand when you're trying to identify what's happening with a positive charge, and if we use our left hand, then that'll give us the direction of the force on a negatively charged particle directly. So if I line up my fingertips with V, and I curl my fingertips towards B, my thumb gives the direction of the force on an electron. If you like doing it that way, you can. Doesn't matter to me. Just make sure that you figure out the directions based on our cross product correctly. Let's see. Yeah, positive, neutral, negative, just like we determined. If you line up electric fields and magnetic fields, you can generate a velocity filter. Velocity filters are kind of fun. This is a really common style of question to show up on AP exams. Velocity filters could be used if you want to create, say, a particle accelerator or particle generator that has a very specific speed. And if you're using a particle accelerator for experiment, you probably want to know exactly how much kinetic energy each of the particles has. So velocity filters are a really important part of that, because they're going to steer off any particles that are a little too fast or a little too slow. So let's think about what happens when I have a positively charged particle that shows up in my velocity filter. Say there's my particle right there. It's moving with a velocity in that direction. What would the forces be on this charged particle? Well, if it's a positively charged particle and it's in an electric field and my electric field is directed downward, then it should be experiencing a Coulomb force in that direction. And I know that the Coulomb force is equal to Q times E. There's also going to be a magnetic force. Assuming that it has some velocity, and that velocity is at least partially perpendicular to the direction of our magnetic field, I'm also going to get a magnetic force. Now, the direction of that magnetic force, I can use the right-hand rule to figure out. So my velocity is this way, and magnetic field is that way, so my thumb gives the direction of that magnetic force. And that magnetic force, remember, is equal to Q, V cross B. There we go. Velocity filter. These forces are balanced. It's a lot like the problem we did earlier where we were balancing the magnetic force and the gravitational force with one another. Here we're balancing a Coulomb force and our magnetic force, Lorentz force. Now, just because one point's upward and one point's downward doesn't mean they're necessarily balanced. They have to be equal to one another. So we can set them equal. We would say that if we have a velocity filter, which means that a particle is going to go through undeflected, then the Coulomb force and the magnetic force balance one another. QVB equals QE. And so we have a specific velocity where particles go through undeflected. And that happens when our velocity is equal to the electric field strength divided by the magnetic field strength. Now you might wonder, what happens if our velocity is just a little bit too big? If our velocity is just a little bit bigger than this E over B ratio, then the magnetic force is stronger on this particle, but the Coulomb force is unchanged. So particles that go through this velocity filter too fast tend to curve upward. Particles that go through just a little bit too slow tend to curve downward. We call it a velocity filter because if we set up our system, we tune our electric field and our magnetic field strength so that we are looking for a specific velocity, that one velocity will go through completely undeflected because the net force on the particles as they move through the system is zero. So my next question for you would be, should this work for negative particles as well? Any ideas? Well, let's go back to our original equation. We said that in order for us to have a particle move through undeflected, that our magnetic field strength and our magnetic field force and our electric field force should be balancing one another. And we said that QVB equals QE, and it looks to me like that charge just completely cancels out. This should still work. The only thing that's different is the direction of these forces. It still is going to filter out particles that have that specific speed. But let's think about the direction of the forces. So if I have a negatively charged particle in this electric field, then that negatively charged particle, and if my electric field is pointing downward, is going to experience an upward Coulomb force. How about our magnetic field strength? Or a magnetic force? So if I have this negatively charged particle, remember we're going to do a right-hand rule. So I'm going to line my fingertips with the direction of the velocity. It's moving this way across the board. And then I'm going to curl my fingertips towards the direction of the magnetic field strength. And my thumb is now giving the direction that the magnetic force would be on a positively charged particle. But this is a negatively charged particle, so it's actually downward. And so our Lorentz force or magnetic force is downward. You also could do this with the right-hand rule and say velocity is directed this way across the board, magnetic field points into the page, into the board, and my thumb is pointing downward. And so when I do the left-hand rule, this gives the direction of the force on a negatively charged particle. I could do this formulation of the cross product as well, and so I'm going to line my fingertip this way with the direction of the velocity. I'll align my second finger with the direction of the magnetic field. My thumb now gives the direction of the force on a positively charged particle, but this is negatively charged, so it points downward. The identity of those forces is flipped, but they're still balanced with one another. All right, I actually think that's probably a good place to stop. So I'll have another video up shortly looking at the forces on current carrying wires. Thanks, Physics C.